Problem 37, page 358. We have an object is moving to the right with initial velocity vi. This object is fired at a solid cylinder of mass m and radius capital R. The cylinder is initially at rest. So, as the initial state, we have only the mass m in motion, and the cylinder is at rest, and is mounted on a fixed horizontal axle that runs through its center of mass. The line of motion of the projectile is perpendicular to the axle and at a distance d, which is less than r. So here we have the distance d, which is less than r. Part 1. Find the angular speed omega of the system just after the object strikes and sticks on the surface of the cylinder. Okay. Let's say at initial state, we have this configuration. Okay. Here we have the cylinder. Here we have the axis at the center of the object. Okay, I take the lateral view of the system. And here we have the mass m. If you see the horizontal axis, as you see, we have a distance d here. This is just before the collision. Here we have the velocity to the right. So, initial state before collision. And after the collision, we have the same system where the object will strike the cylinder at this point, okay, which is at a distance equals d from the center. After the collision, at the final state, the system starts to rotate around the axis with a circular and angular velocity omega. This is after the collision. Find the angular speed omega just after the collision. You know here, summation of tau external equals to dl divided by dt equals to 0. Why? Because we have only the weight of the cylinder will be down, and we have the reaction, we have the weight, and we have the reaction. The weight and the reaction, here we have mg, and here we have n. N and mg pass through the axis. So tau of n and tau of mg equal to 0. In this case, L is constant, and here we have an isolated system. And L initial equals to L final. In the initial state, here we have only the motion of m. Okay? You know, in the case of a translational motion, Here we have L, which is equal to R times M times V. Or we can say R times P. P equals to MV. Anyway, if you want to write in details, we can say here we have R cross P, which is equal to M times V initial. This is the initial state. What about the final state? In the final state, we have a rotational motion. We can write directly, we have a pure rotational motion. So we have I of the system times omega just after the collision. Okay? So here R is the projection of from the center to the elongation of the velocity. What I mean? Look here. Here we have the velocity of the mass m. We can do this line like this, and from the center we can have the projection on the velocity. So this one is r, small r, which is equal to d. So here we have d times m times v initial times sine the angle between r and v, which is equal to 90. So we have 90, which is equal to I of the system times omega. Anyway, here sine 90 equals to 1. What about I of the system? I of the system equals to I of the mass m after the collision plus I of the cylinder. I of the mass m here, you know, which is equal to ICM of the mass m, which is equal to 0. Why? Because the axe is not passing through the small element m, plus m times the distance square between the axis and the center of mass of small m, which is equal to capital R square. Okay? As you see here, the distance between the center of mass of small m and the axis, which is equal to capital R. Okay, plus ICM of the cylinder. I give you the value of ICM of the cylinder, which is equal to half mr square and plus m times the distance between the center of mass of the cylinder and the axis, which is equal to 0. So we can write IS, which is equal to mr square plus mr square over 2. Here we have the value of I. So we can substitute the value here. D times m v initial equals to I mr square plus m r square over 2 times omega. So omega equals to d m vi. We can take 2 as a common. We get 2mr square plus mr square. We can put 2 up. Here we get 2. The final answer here, it can be 2d mv initial divided by, we can take r square as a common factor. We get inside m plus 2m. This is the value of omega after the collision. Part B is mechanical energy of the system of mass m in the cylinder is conserved in this process or not? Do you have a conservation of mechanical energy or not? This is the question. We can say, is the delta mechanical energy equal to 0 or not? You know, as the object after the collision sticks on the cylinder, in this case we have a non-elastic collision. So we can say, in general, we don't have a conservation of mechanical energy. No, because the collision is non-elastic. We can say it's perfectly non-elastic. So some mechanical energy changes to internal energy. Okay. In this case, we don't have a conservation of mechanical energy.